Good evening, everyone. Welcome to the week number 11, that is your second last session related to structure analysis course, wherein we will try to solve the problems that you have covered in the current week. So, this is your second last session, and currently we are analyzing indeterminate structures, wherein we have seen how to solve the problems using slope deflection method. And now, in this week, we will see how to solve the complex structures which are indeterminate in nature using moment distribution method. So let me share my screen first. Then we will see how different problems could occur and what kind of method we should adopt to solve the problems using moment distribution method. Now I hope the screen would be visible to everyone. Let me check it. Yes, now it is visible. So this is your week number 11 for the structure analysis course. And regarding this problems of solving session, so what we generally do, we try to solve the problems related to the topics that you have covered in the current week, in which the topics that you have covered in the current week, we will try to solve some problems related to that, which will help you in understanding the concept more in deeper sense. And using problems, you will help to know what and where you should require to utilize the concepts that you have understand in this current session. Okay, so for the course outline, we have reached in the almost end of the course. We started with the basic thing, analyzing the structures for slope as well as the deflection. And further, we have seen how to determine the shear force and the bending moment diagrams for different structures. So starting with the analysis, we started with the statically determinate structures, in which we have seen three different kind of structures. That is, you have trusses, you have beams, and you have frames. In which we started with the trusses, and we have seen how to analyze the truss, which is determinate in nature, using method of joint as well as method of sections. Then we have seen how we can analyze beams and frames. For that, we have seen different methods, that is moment area method, conjugate beam method, unit load method, virtual work method, and direct integration method, and many more. So depending upon where you can use what method, which is easier to apply for that particular problem, we can utilize that method to solve or analyze the problem. After that, we have moved to the analysis of structures in which moving loads are moving from one point to other. So in that, we have seen that how the proportioning of load should be done so that the maximum shear force analysis as well as the maximum bending moment analysis can be done using Mueller-Bridge law principle. After that, we have moved to the statically indeterminate structures, and in that we started with the force, or you can say the flexibility method, or the stiffness, or you can say the displacement method. In that, first we have differentiated between them, that how you can differentiate between the force and the stiffness method. And further, the same problems which we have earlier solved, that is truss, beams, and frames. Now, when they are indeterminate in nature, then what kind of method you should adopt to solve that problem? We have seen for trusses, we have used method of consistent deformation. For beams and frames, also method of consistent deformation work, as well as moment distribution method, as well as slope deflection method will also work. So today in this session, we will try to solve the concepts using moment distribution method. So for the displacement method, one method we have already covered, that is the slope deflection method, in which multiple problems related to beams as well as frames we have seen in the previous session. So today also we will solve the problems for displacement method, but now we will solve using moment distribution method. So talking about this, we have our first question in which you are expected to calculate the distribution factor of moment at joint E for the span EA and ED respectively for the frame given in the figure, in which EI is same for all the members. Okay, so what you have required to find? You are required to find the moment distribution factor of moment at joint E for span EA and ED respectively. Okay, so how you find distribution factor? First, you will calculate the far end stiffness for each and every joint. Then you will see that for a particular span, what will be the proportion of the total stiffness that will occur on particular span. That will give you the distribution factor for that particular, or you can say corresponding span. So first of all, you should know that for the far end stiffness, when your far end support is hinged, what kind of stiffness you will develop? That will be equal to 3EI by L. In case of fixed end support, when it is far hinged, in that case you will develop the stiffness equal to 4EI by L. And in case when it is free, so in that case your stiffness will be equal to 0. Okay, so let's solve this problem. So in this, at joint A, 4 members are connected. That is your member EA, member EC, member EB, and member ED. Out of which you can see 2 are hinged and 2 are fixed. So we will apply the distribution factor for each and every span that is asked to you, that is for span EA and ED, and then we will get to know what will be the distribution factor. So first we will determine the stiffnesses. So in that, your first span, that is KE for EA span, in which your far end is fixed, so for this case your KEA is equal to 4EI upon L of EA. That means it would be equal to 4EI upon 2 equal to 2EI. Similarly, your end C is also fixed. So in that case, your KEC will also be equal to 4EI upon LEC. And in this case, you can see your LEC is equal to 3. So that will become 4 by 3 EI. Now, your next two joints or your next two far ends are hinged. That means your KEB will have hinged far end so in that case your KEB, I think I should copy this. So if I copy it and paste it here, let me reduce the size. So your KEB will be equal to 3EI upon LEB, and here that will be equal to 3EI upon 1, that will be equal to 3EI. Further, your span ED is equal to 3EI upon LED, and that is equal to 3EI upon 2. Okay, now you have calculated all the stiffness factors. Now you are required to calculate the distribution factor. So we require for span EA and ED. So let me start for span EA. So for span EA, your distribution factor for EA will be equal to K of EA divided by K of EA plus K of EC plus K of EB plus K of ED. Okay, so that will become equal to DF for EA will become equal to, so twice of EI we have calculated earlier, divided by twice of EI plus 4 by 3 of EI plus 3 by 2 of EI (3 by 2 of EI plus 3 of EI. Okay, now you have to solve this. For this you can eliminate E from the equation, and then what will be remaining? Your remaining will be 2 divided by 6. If you take the whole LCM, it would be 6. So that will be equal to 6 plus 8 plus 9 plus 18 divided by 6, and it will give you 2 into 6 upon 7 and 27 plus 6, 33. Let me check this again. Here there is a mistake. It would be 12. Now it is fine. So that means it would be equal to 38 plus 9, it equal to 47. So your DEA will be equal to 12 upon 47. Fine. Now similarly, we will solve for other span, that is your span ED. So for span ED, your DF for ED will be equal to K of ED divided by K of ED plus K of EA plus K of EB plus K of EC. If you solve it, what you will get? So your K of ED that you have calculated to be equal to 3 by 2 into EI divided by your 3 by 2 of EI plus others are 2EI plus 3EI plus 4 by 3 of EI. That means it will be equal to, as we have already calculated it as 3 by 2 into 6 upon 47, and that will give you the value as 9 by 47. Okay, so this is how you will calculate the value of distribution factors. Now if you want to check that whether your value is correct or not, what you can do, you can determine the value of DF for all the spans, and then you can check that their sum should be equal to 1. If the sum of all the distribution factors is coming out to be equal to 1, then you can say that your calculation for the distribution factor is correct. Okay, so now let's move further and we will increase the complexity for this. Okay, now it is same question for you. Now in this question, as for EA and ED, you have already calculated. Now the question is asking you to calculate for EB and EC. So same thing we will apply. Your DF for EB will be equal to K of EB divided by K of EB plus K of EA plus K of ED plus K of EC. Okay, so that will give you the distribution factor EB to be equal to, so for EB it is 3 upon EI divided by 3EI plus 2EI plus 3 by 2 EI plus 4 by 3 EI. If you solve it further, what you will get? You will get DF of EB to be equal to 3 into 6 upon 47, and that will give you the value of DF of EB to be equal to 18 upon 47. Fine. So similarly, for other span, which is your EC span, so for span EC, your DF of EC is equal to K of EC divided by K of EC plus K of ED plus K of EA plus K of EB. Okay, now substitute all the values. So in this you will get K of EC to be equal to 4 by 3 of 4 by 3 of EI divided by all the coefficients. Solve it further. What you will get? 4 by 3 into 6 upon 47. That will give you the value as 8 by 47. So your D of EC is coming out to be equal to 8 upon 47. Okay. So now we have calculated all the distribution factors that was asked in the question number 1 as well as in question number 2. Now if we apply the check for df plus df of EA plus df of EB plus df of EC plus df of ED, and that will come out to be equal to, for EA you already calculated it to be 12 by 47. Next you have to be equal to, for EB, equal to 18 upon 47, plus for EC to be equal to 8 upon 47, plus for ED it is 9 upon 47. So that will give you the value as 12 plus 18, that is 20, 20 plus 8, 28, 28 plus 9, sorry, 12 plus 18, 30, 38, 30 plus 8, 38, 38 plus 9, 47, divided by 47. So that will give you the value to be equal to 1. So that means your all the distribution factors are correct, because your all summation of distribution factor is coming out to be equal to 1. Okay. So let's now, we will try to solve the problem related to moment distribution method, and in which we will see how can we determine the absolute moment that is coming out in an indeterminate structure. So for this given beam, you have to determine the absolute bending moment for a continuous beam ABC. So this is a continuous beam of two span, in which one span is having the length of 5 meter and another span is having of length 2.5 meter. And in this, a span AB is loaded with uniformly distributed load of 12 kilonewton meter. So what is the first step? First step, we will determine the stiffness coefficients, and that will come out. So let's calculate for this. So your stiffness coefficient for BA will be equal to K of, sorry, it will be equal to, for BA far end is fixed, so that will be equal to 4 EI upon L of AB, and that will give you 4 by 5 of EI. Okay, now K of BC will be equal to 3 EI upon L of BC, and that will give you the value as 3 divided by 2.5 EI, and that will come out as 6 by 5 of EI. Now we will calculate the distribution factors. So calculate distribution factors. So the distribution factors will come out as df of BA will be equal to K of BA divided by K of BA plus K of BC, and that will give you the value as K of BA to be equal to 4 upon 5 EI divided by 4 by 5 EI plus for BC we have calculated it as 6 by 5 EI. So if you take the LCM further, you will get it as 4 divided by 6 plus 4 equal to 0.4. So your DF for BA came out as 0.4. So how you will calculate for BC? You will use the same formula K of BC to be equal to K of BC plus K of BA. And now this will give you the value as 6 upon 5 EI divided by 4 upon 5 EI plus 6 upon 5 EI, and that will be equal to 6 divided by 4 plus 6, and that will be equal to 0.6. Okay, so if you add both of them, you will get the value equal to 1. That means your answer is correct. Now you have to find the absolute, we can say absolute bending moment at different ends. So what you will do? We will start with calculating of fixed end moment. Now calculating fixed end moments. So in this, for span AB, how it will look like? It will be equal to minus WL square divided by 12, and the value will come out as minus 12 into 5 square divided by 12, and that will be equal to minus 25 kilonewton meter. So now your M for BA will come out as 25 kilonewton meter. Similarly, we will calculate for MBC. So your MBC in this case will be equal to MCB equal to 0. Now we will solve by calculating the moment distribution factor. So now using moment distribution method, okay, so let's see how we will solve this problem. So first we will mark joints. So this is your joints. Now what are your members? So members have AB at joint A, and you have BA and BC at joint B, and CB at joint C. So that will become your joint B, and this will become your joint C. Now we will define the distribution factor for each member. So in this case, AB is a fifth member. So in this distribution will be 0. For BA, we have calculated it to be equal to 0.4 and 0.6 respectively. And in case of C, so since it is a hinge end, so you will get the distribution factor to be equal to 1. Fine. Now write the fixed end moments. So the fixed end moments in this case will come out as, we have calculated it as minus 25, 25, 0 and 0. Okay, so let me partition this. Okay, fine. Now in this, you can see in the joint B, you have the distribution to be equal to plus 25. So what we will do, we will divide this plus 25 in terms of distribution factors. So that will give you the value equal to minus 10, and this will give you the value as minus 15. Fine. So in this is your distribution factor, and then its carryover will come out as minus 5, and for this the carryover will come out as minus 7.5. Fine. Now if you do the total, what you will become, you have here equal to plus 15, here it is minus 15, here it is minus 7.5, and here it is minus 5. Okay, now what will become, in this you can see that joint E will have 0 moment. So for this case, what it will become, in this, if we add the plus 7.5, that will give the carryover of plus 3.25, 3.75 in the BC. So if that will give the corresponding 3.75, okay, I think I will write one step down. So if that will give the corresponding 3.75 in this equation, so your next thing, that is, it will become, so now you have to divide. So now let's calculate it further. So what it will become, I think I should copy this thing. I don't know whether it will happen or not. So now what it will become, 0.375 you have already mentioned. Okay. So your total after this step will become minus of 30 plus of 15 minus of 11.25 and other is 0. Now again you have got the balancing moment to be equal to 3.75. Now you have to divide this 3.75 in this as per the distribution factor. So if you divide the 3.75 in the terms of distribution factor, it will come out as minus 1.5 minus 2.25. Okay. So if you divide in terms of this, their carryover moment will come out as minus of 0.75, and in this it will come out as minus of 1.13. Fine. Now we have to remove this 1.13, like previously 7.5 we have done. So if we have to make it to be positive 1.13, that means it will give a corresponding value of 0.75, sorry, 0.57 as the additional disturbance. Okay, so now this 0.57 can be distributed as 0.228, or you can say minus 0.23, and here it will come as minus 0.34 in the equation, and their corresponding values will give as 0.12, and here also it will come as 0.17. Okay, but if we are totaling it here, what we will get the value? We will get the value as 30 minus 30 plus 0.75 minus 0.75 plus minus 0.12. You will get the value as 30.87. Let me paste it again. So the value will come here as 30.87 in negative. And you can see here 15 minus 1.5 minus 0.23. It will give you the value as 13.27. And the corresponding other values will come out as minus 11.25 minus 2.25 plus 0.57 minus 0.34, and it will give you the value as minus 13.27. And last value, it should be equal to 0 because that is a unit end. So that will become your final fixed end moments for this question. Okay, so we can end this here. Yes. Okay, so that means you have calculated all the fixed end moments at different points of the continuous beam. Now the same question is there, but in this question it is so further it is also mentioned to calculate absolute bending moment at A, so that we have missed. So after calculating the moments, you have required to calculate the fixed end moments at A. So what you will do, you will draw the free body diagram. So in the free body diagram you can see, let's see, you have uniformly distributed load. Like this, and what kind of support will be there? So in this, reaction will come out as VA and VB, And in this case, you can see the moment to be negative. That means anti-clockwise movement will occur equal to minus 30.87. And here clockwise movement of 13.27 will come. Okay. Now, in this case, if we take summation of moment so what is I asked you in this question? You have asked to calculate absolute bending moment. So absolute bending moment you have already calculated it to be equal to 30.87. So okay. So let's make this question in here. We will solve for the next question. So next question is the same continuation of the previous question. In this, it is asked to you to calculate the reaction force at support C. So if you are expected to calculate the reaction force at C, so what you will do? You will draw the free body diagram of the structure. So in this, you will get VB, you will get VC, okay. And what is the moment coming here at BC? For BC, it is minus 13.27 kilonewton meter. So this is your B, this is your C. So if you take summation of moment about C, or yeah, if we take summation of moment about B to be equal to 0, that will give you minus 13.27 and minus of VC into what is the length? That is 2.5 to be equal to 0. So from this, you will get the value of VC to be as minus 13.27 divided by 2.5, and that will come out as equal to minus 5.308. Okay, so this is your reaction force at C. So if we draw the free body diagram for this case, so it will become like this. You have this free end. In this, you are having this reaction VB. Here also one reaction will come, that is VC, and it has the value equal to 5.308 kilonewton meter. So if this is 5.308, that means here also the reaction will be 5.308 kilonewton. Okay. Further, here moment is also there. That is the anti-clockwise moment of 13.27 kilonewton meter. So this is your end B and this is your end C. So if you also take, if you want to check that what is the value of, so check, how can you do that? Take summation of moment about C and it should come out to be equal to 0. So if you find the moment, the VB into 2.5 minus 13.27, what is the value? So your value is 5.308 into 2.5 minus 13.27, and that will give you equal to 0. So that will check and provide you that your solution is correct. Fine. Now let's move to another question. In this is the same continuation of the previous question. It is asking you calculate the absolute bending moment at C of the given frame. No, this is another question. Sorry. So let's solve this question. Again, absolute bending moment of a indeterminate frame. It is asking to you. So what you will do? You will use the moment distribution method to solve the problem. So first, what is the step? We will find the stiffness factors. So for KBA, your value will come out as 4EI divided by L of BA. That will be equal to 4EI upon 18. That means 4 upon 18 equal to 2 upon 7, 2 upon 9, and that will come out as 0.222 EI. Okay. Similarly, you try to calculate for K of BC. So your K of BC again will come out as 4 EI upon L of BC. Your L of BC is 9. So that will be 4 by 9 EI, and that will be equal to 0.0444 EI. Okay. Now your distribution factors you have to calculate. So calculate distribution factors. So how you will calculate the distribution factors? You will take df of BA to be equal to K of BA divided by K of BA plus K of BC, and that will come out as 0.222 EI divided by 0.222 EI plus 0.444 EI, and this will give you the value as 0.222 divided by 0.666, and that will give you the value equal to 1 upon 3. Okay. Now further, if you try to calculate the value of df of BC, it will give you the value of 0.444 EI divided by 0.222 EI plus 0.444 EI. It will give you the value as 0.444 divided by 0.666, and that will be equal to 2 by 3. Now the next step is to calculate fixed end moments. So your fixed end moments in this case will come out as M of AB will come out as minus WL square divided by 12, and that will give you the value as minus of 4 18 square divided by 12, and that will come out as minus 108 kilonewton meter. and that will give you the value of m of BA to be equal to plus 108 kilonewton meter. If I talk about m of BC and m of CB, that will come out to be equal to 0. Now again make the chart for different joint members, distribution factor and fixed end moments. Okay, so that will come out as AB, BA, BC and CB. This joint is A, this joint is B, and this joint is C. So here the distribution factors are, as we have already mentioned, it will come out as, for the fifth end, it will come out as 0. For BA, we have calculated it as 1 by 3. And here it will come out as 2 by 3. And other end is also fixed, and that will be equal to 0. And your corresponding fixed end moments will be minus 108, 108, and rest are 0, 0. Now you have this 108, you have to distribute in terms of the distribution factors. So if you do the distribution of 108, so 108 divided by 3, it will come out as 36. So minus 36 and minus 72 will come here. Now their corresponding carryover moment will come in this side. That will be equal to 18. And here it will come out as minus of 36. Okay. So if you do the checking again, that whether it is satisfied or not. So minus 108 and minus 18, it will come out as minus of 126. 108 minus 36 will give you 72. Here it will come as minus 72 and minus 36. Fine. So that means we can end it here in the first step only. So this will give you the absolute moments at different points in the section. Okay, so now what is asked to you in the calculation is the absolute bending moment at C. So the absolute bending moment at C will come out to be equal to minus 36 kilonewton meter. Okay. Now the same question is asking you to calculate the absolute shear force at A. So it is asking to you to calculate absolute shear force at A. For the calculation of absolute shear force, what you will do, you will draw the free body diagram for this case. This is your VA, this is your VB, and I am marking the loading here to be 4 kilonewton per meter, and the moments that we have already calculated here is the negative 30.87, that means anti-clockwise moment of 30.87 kilonewton meter, and here the clockwise moment of 13.27 will come. So this is your joint A, this is your joint B. Now what is expected to you? Calculate the shear force at point A. So for that, what we will use? We will use the summation of moment about B to be equal to 0. Okay. So if we take summation of moments about B to be equal to 0, that will give you first negative 30.87 plus positive 13.27 plus VA into what is the length? Length here is 18 meter. Okay, and the loading will also come as negative. So 4 into 18, and at how much distance it will come? 18 by 2, and that will be equal to 0. So you add up everything, you will get here as minus 30.87 plus 13.27. That will come out as minus 17.6 plus 18 times VB, and minus of this 18 into 2, it will come out as 648 equal to 0. Now if you solve for VA, I have written wrongly here, VA. So if you solve for VA, you will get the value of VA as 36.9778 kilonewton. Oh, I think I have written the wrong values. Let me check. For A it is, how I have written these values? All these values are not correct. I think I have taken from different source. Let me check. This value is, sorry for the interruption again. So these values are different. So this value we have calculated as 126 and 72. So this will come out as 126 and this will be 72. Fine. Now let me check it here. So that will be minus 126 and 126 and 72. 126, 126 and 72. Okay, that will be minus 126 plus 72, and this will come out as minus 54. Okay, so now if you try to solve it, you will get the value as you will get the value exactly 39 kilonewton. So this value is 39 kilonewton. Okay, so you will get the value of VA to be equal to 39 kilonewton. So this is how we will calculate the absolute shear force at different points of the beam. Okay, so let's see what is the other question. So now other question, you have a frame element. You have to calculate distribution factor for segment BC. Okay, so let's solve this question. So in this question, what we will do, we first find the stiffness coefficient. Okay, so how we will do that? So in this, your K will come out at KBA, and that will come out to be equal to, since the far end is hinged, that will come out as 3EI, and here I is also 2I, so that will be 3 into E into 2I divided by L, that is 5, that will be equal to 6 upon 5 EI. Fine, I will write it in decimal form. It will be 1.2 of EI. Now next we will calculate for BC. So for BC, it will be equal to 4 EI by L, and that will come out as twice of EI. Fine. Now next is, you have to calculate for BE. BA and BC we have calculated. Now we will calculate for BE, and for BE it will come out as 4EI upon 4, and that will be equal to EI. Okay, now for joint C, okay, if you want to calculate for BC, we can calculate here only. So for BC, so distribution factor for BC, it will be equal to K of, distribution of factor of BC, it will be equal to K of BC divided by K of BC plus K of BE plus K of BA plus, no, that's all. 3 joints are there, we have written. Now for KBC, we have calculated it as twice of EI. So twice of EI divided by twice of EI, BE we have calculated as EI, and for BA it is 1.2 EI. So that will accumulate it as 2 divided by 4.2, and it will give you the value as 0.476. So your distribution factor for BC will be like this. Okay, so we have calculated the distribution factor for BC. Now let's see what other question is telling you. Now other question is telling you directly to calculate the reaction force at support A. So for calculating the reaction force, we have to solve first the whole frame, then only we can calculate the reaction force. So now we have only calculated the distribution factor for BC. Now we have to require to calculate distribution factor for other spans also. So let's calculate that. So your distribution factor for BA will be equal to 1.2 of EI divided by 1.2 of EI plus twice of EI plus EI, and it will give you the value as 1.2 divided by 4.2 . So by this you will get the value of distribution factor of BA to be 0.286. So earlier we got it as 0.476. Now we got it as 0.286. So 2 you have already calculated. Third we will calculate now. So our third distribution factor, that is distribution factor for BE, will come out as EI divided by, now I am writing it completely, that is 4.2 EI, and it will give you the value as 0.238. Else I have one more method, that means BE will be equal to 1 minus distribution factor of BA minus distribution factor of BC. By that way also I can calculate that. Now I have calculated distribution factors for all the spans at joint B. Now let's calculate the distribution factor for span B, CB, CD, and CF. So for that, first we will require to calculate coefficient CF, and that will come out as, for CF it will be 4 EI upon L of CF, and that will be equal to 4 EI upon 2 equal to twice of EI. So the distribution factor for CB will come out as K of CB. So you have K of CB to be equal to twice of EI divided by twice of EI plus, for CF it is again twice of EI, and third for CD that will be equal to 0. So from this you will get the value as 0.5. Okay. Now your distribution factor for CF will be equal to twice of EI divided by again twice of EI plus twice of EI plus 0. 0 is coming here because of the cantilever span of CD, and that will give you the distribution factor equal to 0.5. Fine. And third, your distribution factor for CD, it will be equal to 0. And rest are also there. That is your distribution factor for AB will be equal to 1 because hinge support is there. Your distribution factor for EB will be equal to your distribution factor for FC plus or equal to distribution factor for CD to be equal to 0. Now what we will do? We will calculate fits and moments. So if we try to calculate the fits and moments, what we will get? Let's see that. So your fits and moment for MAB, it will be minus WL square upon 12, and that will give you the value as minus 2 into 5 square divided by 12, and it will be equal to minus 4.17 kilonewton meter, and that will give you MBA bar equal to 4.17 kilonewton meter. Now for span BC, your MBC will become minus WL square upon 12, and that will become minus 2 into 4 square divided by 12, and that will be equal to minus 2.67 kilonewton meter, and this will give MCB bar to be equal to plus 2.67 kilonewton meter. Further, this MCD will come out as minus of 8 into 3, that will be minus of 24 kilonewton meter, and rest are minus, that is M of FC to be equal to M of EB, and that will be 0. Okay, same for M equal to M of BE equal to M of CF. Fine. Now all the fits and moments we have calculated. Now what we will do? We will draw the table and calculate the moment distribution factors for this case. So in this, first we will write the joint. Next your member. Then the distribution factor. And then we have fits and moments. These are the first basic things that you have to write in this. So first you have member AB, then you have BA, BC, BE, and further you have, this is at joint A, this is at joint B. Now for joint E, I am writing here it as EB. For joint C, we have 3 more values, that is CB, CD, CF. These are your joint C. And finally, your joint F is having one value, that is FC. Their corresponding distribution factors, as we have already mentioned, that will become 1.286, 0.476, 0.238, then 0.5, 0.5, and 0. Okay. Now their fixed end moments will become minus 4.17, 4.17, minus 2.67. Here we have 0, 0, 2.67, minus 24 due to that cantilever load, and again 0, 0. Okay. Now what you will do first? You will first balance A part. So if we try to balance A part, in that A part, it should be, you should have 0 moment, but here minus a negative moment is coming. So what you will do? You will make it 0. So if you make it 0, its corresponding carryover moment will also come. So their carryover moment, I will mark the lines, horizontal lines. I think that will be easy for us to understand that. Okay, so its carryover moment will come out here is as 2.09. Fine. So here 2.09 will come. Now next we will balance B. So if we balance B, we have to add this 2.09 in this whole equation. Okay. So how we will do? First we will take this 4.17 plus minus 2.67 plus 2.09. So out of this, we will divide it into in terms of distribution factor, and it will come out as minus 1.03, minus 1.71, minus 0.85. Okay. If we further balance it, no, now carryover will come. So carryover for balance CO, I think I should mark multiple lines. Okay. Now the carryover moment, because of this distribution loads, will become, so here 0.85. So 0.85 will give as the same value to CB, and that will become minus 0.85, and here the corresponding carryover will come, that will be 0.43. Fine. Now we will balance section C. So if we try to balance the section C, what it will become? So here you have, in terms of additional minus 24 plus 2.67 plus minus 0.85 will also come, and then your distribution factors will become 11.10, 0, and 11.2, Okay, so for this 11.10, the carryover moments will become 5.55 here, and for BC also it will come as 5.55. Okay, so let's continue it in next page. I think I should copy this whole page only. Okay, so let's solve them by removing the additionality that we have to make it again. Okay, so till 5.5 we have reached. Okay, now we have to do the balancing of again B because of this 5.5. So now 5.5 will have come. So we have to balance this section. So now due to this 5.55, the balancing will be 1.59, 2.64, and 1.31. We can check their total will come out as 5.5. And then here also carryover moment, carryovering will occur same as minus 1.31, and here it will be minus 0.66. Fine. Now due to this 1.31, again we have to balance the section C. So if we balance the section C, it will become 0.66, 0 and 0.66, and their carryover will go again in the cyclic manner as 0.33 and 0.33 in BC. So 0.33 will come in BC also. Okay, now we finally balance B. So if we try to balance the B, it will come out as minus 0.09, minus 0.16, minus 0.08, and this 0.08 will go as carryover in CB, and this will add half carryover will go to EB. Now if we try to make their total, so their total will be, let me mark it in the next page. So their total will come out as now I am writing final the total. Okay, so the total final value will come out as, in this case A, it will be 0, that we have already done in the first step. Here it will come out as 3.55. Here it is minus 1.30. Then we have minus 2.24. Then minus 1.13. For CB, it will be 12.17. For CD, it is minus 24. For CF, it is 11.76. And finally, for FC, it is 5.88. Okay, so this will complete the problem for calculating the different absolute moment at the section. Okay, now finally the next question is telling you, okay, in this question also one thing is mentioned, you have to calculate the vertical shear at support A. So for calculating the vertical shear at support A, how you will do, we will make the free body diagram of the section. So if we make the free body diagram of the section, it will come out as like this. In this, let's mark the vertical reactions as this. this is your VA, this is your VB. You have the loading over the structure. Okay, so this loading is 2 kilonewton per meter, and on the left side you have zero moment, but on the right side you have the clockwise moment of 3.55 kilonewton meter. This is your joint A, this is your joint B, and your total length is 5 meter. Now what we will do, we'll take summation of moment about A to be equal to 0, because we require, okay, so if we require at A, what we can do, we'll take summation of moment about V to be equal to 0. If we take that, what we will get, we'll get VA into 5, okay, minus of 3.5, sorry, plus of 3.55, and then minus of 2 into 5 into 5 by 2 equal to 0, and that will give me value of VA to be equal to 25 plus 3.55, 25 plus 3.55 divided by 5. It will give me the value as 5.71 kilonewton. Okay, so you have calculated the reactions. Now the next question is the continuation of previous question only. In this, it is telling you to calculate the absolute bending moment at E. So absolute bending moment at E you have already calculated. So absolute bending moment at E, as you can see from the figure, yeah, from this, at E joint you have calculated the value as minus 1.13 kilonewton meter. Okay, so whatever you require, whether it is shear force or absolute bending moment, you can calculate for any complex structure using this moment distribution method. Okay, so let's wrap up this session. So today what we have done, we started with analysis of indeterminate frames or continuous beams using moment distribution method. So what is the first step that is involved in this? So first step is involved in this is to calculate the coefficients. So stiffness coefficients we have calculated depending upon the far end conditions at different joints. Then after calculating the stiffness coefficients, we have seen how we can distribute them along the span. So for that, we have determined the distribution factor. So after determining the distribution factor and further calculating the fixed end moment for each span, we have utilized the concept of moment distribution method for each span, and then we have calculated the absolute bending moment at each joint of the span. Okay, so after calculating the fixed and absolute bending moment, so whatever shear you require to calculate for each span, or whatever you can say reaction force you are required to calculate, you can calculate by this method using the simple free body diagram concept. So this will wrap up your analysis of indeterminate structures, both by slope deflection method as well as the moment distribution method. So next week we will see a review of the concepts relating to flexibility matrix method as well as your stiffness matrix method, or you can say displacement matrix method. So till then, try to solve the problems related to moment distribution method, and whatever doubts you have, you can ask them in the discussion forum provided to you in the Swayam portal. Okay, so thank you everyone. Have a nice day. Enjoy your weekend.
Thank you.